So, you are taking notes on 2.3, the properties of water. And so, the first thing that they talked about in this section was the fact that oxygen is a little bit more electronegative, and it holds the electrons a little bit longer. So this is called a delta, a lowercase delta. This stands for partial charge. All right, it looks like a deflated letter D. All right, so this is a partial negative. When the oxygen holds the electrons a little bit longer, it becomes partially negative. The hydrogens, they give up their electrons a little bit longer, so they become partially positive. So that makes one side of the molecule negative and one side positive. That becomes what's called a polar covalent bond. If they share everything equally, then it would be a non-polar covalent bond. But the beauty of this, that straight line right there, that's the actual polar covalent bond. So there will be questions on the quiz that will ask you, what's the bond between the oxygen and the hydrogen in one water molecule? That is a polar covalent bond. Now here's the tricky part. What's the bond between one water molecule and another water molecule? Do you see the dotted line?
Hydrogen bonding.
That is a weak hydrogen bond. It's not even a real bond. It gets a dotted line. It's not. This is stronger. That's all.
Is it weak because it's like adhesion, right? They're like stuck to each
Yeah. That's a property because of that. Now look, this magnet is not glued to the board. Hence, it's a magnet. It's magnetic. So that's a weak attraction. The glue holding the magnet in the plastic obviously is stronger. So these weak hydrogen bonds are almost like these magnetic bonds. They do the trick where they hold the magnet there, but they're easily broken. And so it also talked about DNA being held together by these hydrogen bonds, which is really good because you have these nitrogenous bases on the DNA, but they can easily be unzipped, so you can copy the DNA or read the DNA, and then they can be zipped right back up again, and that's due to hydrogen bonding. All right? There's going to be a trend that you're going to start to hear when I ask you about these properties. Okay? Let's see if you can pick it up. Now, high heat capacity. Water does not change temperature very easily. So in the summer, from the winter months when it was cold, the water slowly goes up in the ocean, so it actually keeps it cooler in the summertime. And then after the summertime, when the water gets all heated up again, then the winter starts to come and the warm water keeps it warmer by the coastline. Here for us in Central Florida, the temperatures can change a lot quicker. Or states that are totally gridlocked with no water, their temperatures can change a lot more rapidly than when you live near the waters. So that's high heat capacity. Now, high heat of evaporization or vaporization, this is the fastest molecules are the hottest molecules, right? Yes. So the ones that are moving fast enough to actually break the hydrogen bond, they leave first. And so if they are the fastest moving ones, how are they temperature-wise? The fastest ones are the hottest. And so as the hottest molecules leave your body, when they evaporate, what does that leave behind then? Keep going. If the hottest ones evaporate, what does it leave behind? The colder ones. So it slowly is cooling you off. It's slowly cooling you off. Now, Florida is a bummer because Florida is hot out and it's humid. And so it doesn't evaporate very quickly off of your skin. Because it's so humid, the water just doesn't evaporate, the sweat doesn't evaporate. So you can't cool off as quickly. But right when you come inside to a controlled environment where the humidity is controlled in this classroom, and you lean against the chair on your back, right away, what is it?
Cool.
It's freezing cold because it starts to evaporate a little bit more easily in here. All right, the humidity in your rooms are controlled by the air conditioning. Okay? So, what's the reason for the high heat of evaporization? What's the reason?
Oh, because
The reason is hydrogen bonding. Okay? Because the fastest molecules are moving fast enough to break those hydrogen bonds. So here we go. Water is a universal solvent. And it talked about hydrophilic things and hydrophobic things. Some of the things that are hydrophilic or water-loving are ionically bonded substances like salt, NaCl. So the Na is positively charged in the ion solution, and Cl is negatively charged, and actually breaks those ionic bonds and surrounds them with the water. So the positively charged Na is surrounded by all the oxygen sides around it, and it's happy. And the negatively charged chlorine is surrounded by all the positive hydrogens, and it's happy. So water is really good at dissolving things. Okay, and then it also talked about, I don't know, nitrous. It was something NH3, I think. All right, that is also polarly, what is it? Ammonia, NH3, yes. That is also a polar covalently bonded substance, and so that also is hydrophilic. Now, hydrophobic things, what does not mix well with water?
Oil.
Oil. Gas, I guess you're saying? All right. So it's a non-polar substance, and it does not mix very well with the water. It's hydrophobic. All right. So what tends to the properties of that property? What charges and which are due to what's this? Okay, hydrogen bonding and the polarity of the water. Polarity is the key. All right, now cohesion, adhesion, and surface tension. So I have this projected up here. What is it doing?
Floating.
Floating. There's a paperclip floating on the surface of the water. Did you know the paperclip would float if you didn't remember it from bio class?
Yes.
Paperclip float because why?
Surface tension.
Water is denser.
Surface tension. What's happening?
It's not.
What's happening?
Is light enough so it's not sinking.
And what's holding each water molecule together?
Bonds.
Hydrogen bonds.
Hydrogen bonds. They're attracted to each other. And so the water molecules are cohering to each other. When water is cohering to another water molecule, it's called cohesion when they're sticking together. When water sticks to something else like tape, adhesive tape, when you stick it to something else, that is adhesion. So if water sticks to a glass slide, or if you've ever had your water glass at Outback, we'll say, and it's on the coaster and you pick up the drink and the coaster is sticking to the cup, the water is sticking to the coaster and holding it. That's adhesion. All right, water is acting like the glue in that situation. All right, so surface tension is the cohesion of the water molecules due to what type of bonds? Hydrogen bonds. Very good. Now, finally, when you freeze water, all right, put your hands like this for me. This is liquid water. Do you see how it's liquid and moving around everywhere? Do you feel how close your hands are? They're rubbing on each other. They're close. Now pop it like this. Now you freeze it. All right? They're not touching anymore. The hydrogen bonds hold them away from each other, creating what's called a crystal lattice. The crystal lattice, because they're not touching and there's a space right here, all right, this is less dense than the liquid water. There's not as much space between the molecules when it's liquid. But when you lock it into a solid, it's less dense. So what does ice do? Float, which is really important to life because when it freezes, it goes to the surface and protects all of the living things below and lets them still stay in liquid water below. All right, they think that water is the most crucial element to being able to have life on any planet. And it's because of all these properties. There's two reasons why water has these properties. One is polar covalent bonds, and the other is hydrogen bonding. All right, so that's the major lesson today. Thank you, John.
Welcome.